Yeah, thank you all. Thank you for joining the presentation. I am Sanket Kalamkar. I am a postdoc at Inria. I'm working with Professor Francois Bacelli. And this work is in collaboration with our Nokia Bell Labs colleagues at Paris, Fuad, Andrea, and Luis. And so this work is done at Links after Fuad, Andrea, and Luis joined Links. And in this work, we will focus on the beam management in 5G, and we will show that using the mathematical tools from stochastic geometry, we can in fact do uh, quite a elaborate modeling and analysis of this beam management technology in 5G. So this work is supported by the ERC Advanced Grant. And yeah, so just on the technical part, that this work is basically, we know that 5G is a upcoming technology, and where beam management is a key aspect of 5G. And then here in this talk, we will focus on this, what is the motivation of beam management, then the system model for this beam management and assumptions and then approximations that we make. Then we will provide the tool, use the tools from stochastic geometry and show that we will get very nice analytical expressions of key performance metrics in wireless networks. And then we will show systemic trade-offs using numerical results, because at the system levels analysis, there are quite a lot of parameters that depend on each other and they affect each other. And then we will show the trade-off among those parameters and then their effect on the performance of the beam management. And then we will, at the second part of this talk, focus on the interplay between the stochastic geometry and its use in standardization. So we will show how the tools from stochastic geometry can be used or facilitate the standardization process, or it can be helpful in standardization. And then finally, we will conclude the talks with some future directions. So the motivation first. Now, in traditional cellular networks such as GSM, the base stations form a single beam from each panel. So if you see here in this figure, so each base station in each sector, there is a one beam that serves the user equipment or the users that lie inside this cell. Similarly, the users lie in this cell is served by this beam. And as we see that, this is a basically heat map. And as you see that as the increase, there is an increase in the distance of the user UE from the base station, the received power falls with the distance. So red is the highest received power, and then the blue at the edges of the cell, the UE that are at the edges of the cell receive the smallest power. And then in this traditional network, the user equipments are also assumed they are omnidirectional, that they receive from all directions. Now there are critical, the intercell mobility is quite critical in these traditional cellular networks, and which can be done via intercell measurements. So intercell measurements, if a UE is moving across this cell boundary, then it measures its connection, the signal quality with the current serving base station. And then once the received signal quality falls below some threshold, or it keep measuring the signal quality, and then it hands over to the next best station. So if it's moving across the boundary, and probably at this boundary, the UE receives the better signal quality than this base station already serving base station, and then it hands over to the new base station. But now what happens at the edges, especially at the cell edges, there might be a radio link failure. If the signal quality drops below a certain threshold before handing over to a new base station, then the connection with the connection of the UE with the network is lost. So that is what we call radio link failure. And now what happens here in handover procedure, it involves, it is a quite an exhaustive process. It involves measurements and then a lot of communication on the control channel, and then which leads to overhead. So UE and the base station, they have to spend some time doing this handover, and there is a time overhead due to this handover procedure. Now in 5G NR, which is new radio, so it is mostly beam-based radio access network. So basically what I mean by beam-based here is that now if we take one cell here, now instead of only one beam, we have multiple beams serving the user equipments. So for example, if the UE lying this here will be served by, probably will be served by this beam, while the UE lying here will be served by this beam. On the other end, the previous case, the UE lying through in this cell in the traditional cellular networks, the UE, all UEs in this cell were served by the single beam. But on the other end, the beam-based radio access networks, the different U is located at different location might be served by different beams. Now, the advantage of this beam is that these beams are quite narrow, and then basically the transmitted energy by the base station is concentrated is only on that particular direction. As a result, as we can see that even at the cell edges in beam-based cellular structure, we see even at the cell edges we see quite a high received power compared to the traditional cellular network based on the single beam system. So these beams can be generated using the multiple antennas, and then there can be multiple beams per panel. And also the UEs can also be associated with the, can be having with multiple panels or multiple beams. Now, we saw that in the previous case, in the traditional cellular network, intercell mobility was a key. But now in beam-based RANs, the radio access networks, intracell mobility also matters. For instance, if a user is moving along this direction here, so it passes through the different beams, and as it passes through the different beam, the signal quality changes. So it cannot be associated with only one beam. As the UE moves, it has to keep reselecting the beams as it moves. Finally, so basically here this beam selection is corresponds to this intercell mobility as the UE crosses a cell boundary and connects to a new base station. So it selects the beam with that new, the best beam with that new base station. So probably through beam sweeping. And so again, there is there is a cost associated or overhead associated in selecting such beam. Now, once the UE is within the cell of a base station, now in intracell mobility, it travels through multiple beams, and then as it travels through multiple beams, it has to reselect the beams, the best beam, according to the location of the UE and then the quality of the beams. And then also the another concern is here is the beam failure detection. What happens if the beams are too narrow here? Now, what happens? There is quite a possibility that there is a sudden coverage loss as between two beams, and due to that, and it is important to detect such coverage loss, and then the UE should select the new beam as quickly as possible. It should detect that failure of the coverage, detect the coverage loss, and then detect a new beam again. Now, the simpler picture will be here as which we call beamforming technique. So where there are highly directional beams where the energy is concentrated in these narrow directions, and then the receiver here receives a much higher energy from the transmitter. Now, this beamforming should be robust to under mobility condition, whether there is a pedestrian or there is a vehicular speed. So for different speeds of the UEs, this beamforming, whether the beam selection or the beam reselection, should be robust. Now, the performance, as I said, like there could be coverage losses, and there will be overheads associated with this beam selection. Also, there are the wireless channel fade, uncertainty associated with wireless channel and fading, path loss. So all these factors together affects the performance, and then it is important to have a robust beam management system. So for example, if the UE moves, it should discover and quickly switch the beams to maintain the quality of service. Now, there are key challenges in the beam management. One is the beam selection. As I said earlier, when a UE move across different cells, it has to select the beam. And when it is inside the cell, it has to reselect the beam as it travels within the cell. Now, and it has to detect the beam failure and then recover as soon as possible. Now, all these three operations lead to some signaling and delay overheads. So the UE has to be in constant communication with the base station in order to select the beam and changing the beams. So there will be a lot of signaling and the time overheads associated with these procedures. So basically, the beam selection is the search for an appropriate beam with the new base station, which happens during the base station handover, and it leads to the base station handover overhead. And then there is a beam reselection as the UE enters in the new beam, which leads to another overhead. And these overheads basically reduce the time that is available for the data transmission. So which can in turn affect the throughput achieved by the UE. Now in 5G, another key feature of 5G is the availability of the larger bandwidth in mmWave range. So basically, this figure here shows the spectrum available. So we can see that the traditional cellular networks have been operated in this frequency about 800 megahertz and then 2 gigahertz, and then we have this Wi-Fi operating at about 2.4 gigahertz. And then this on the left side on this bottom figure, that we see that this is where the millimeter wave range starts. So about 28 gigahertz has been proposed to use. And then the advantage of this wave, millimeter wave, is that, which is also known as the frequency range 2 or FR2. So there is a large chunk of spectrum available in this wave band. Basically, for the cellular networks, probably on the sub 6 gigahertz, which is around this 3 gigahertz or about below 6 gigahertz, the bandwidth is limited to 100 megahertz. But on the other hand, in mmWave, the maximum bandwidth that can be used is 400 megahertz. So increase in the bandwidth allows a UE to achieve a higher throughput. Also, the sub-6 gigahertz, which is known as the frequency range 1, which is FR1, it provides the better coverage compared to the mmWave bands. Now, the beamforming that I discussed earlier can be used in both mmWave and sub-6 gigahertz. So the key distinction of 5G from the 4G is that for the sub-6 gigahertz bands, the beamforming can be even used on control channels. So that is a key distinction between the 4G and the 5G. Now, the challenges for the mmWave are, there are some critical challenges. For example, if we have an isotropic transmitter, which radiates energy in all directions, so for the mmWave, where the frequency is quite high, the aperture is smaller, so compared to the aperture for the sub-6 gigahertz. And then due to that, the incident energy will be smaller compared to the sub-6 gigahertz. So basically, the smaller wavelength leads to smaller captured energy at the antennas. For instance, if you move from 3 gigahertz to 30 gigahertz, that leads to 20 dB extra path loss due to the smaller aperture here. Now, at the same time, also, since mmWave use larger bandwidths, so it leads to the higher noise power and so the lower signal to noise ratio. So, for instance, if we move from 100 megahertz, which is for the sub-6 gigahertz bands, to 400 megahertz bandwidth, which is for the mmWave, which it leads to the 6 dB of extra noise power. Although despite these challenges, mmWave is quite suitable candidate for small cell deployment, because as we saw earlier, that if the beams are very narrow, the energy from the serving base station will be higher. But at the same time, the interference from the interfering base station also will be restricted, because those interfering base stations will be pointing to a specific direction. And also, it can due to this small cell deployments, it can be used for the network densification and boosting the capacity. So we can overcome the challenges for the mmWave with the use of large array of antennas. For instance, if instead of radiating the energy in all directions, so we can use the multiple antennas or antennas at the directional transmitter, and which points is the transmission towards a specific direction, towards the UE. And also, there is a possibility of using multiple antennas. So these grids denotes the antenna here, and then there can be multiple antennas at the receiver. So with the use of this antenna, the aperture of the mmWave can be increased. And basically, due to this directional transmission, this beam towards this UE, the transmitted energy towards the receiver is also increased. So basically, the large areas of antenna, we can use the large area of antennas to improve the gains. Now, another advantage with mmWave is that because the wavelength is small at mmWave, we can accommodate a larger number of antennas in the same space. So which allows us to create very narrow beam towards the receiver. Now here we motivate why we use spatial model or stochastic geometry for the analysis. Now the motivation behind the spatial model can be seen in these figures. For instance, we have this realization. So we are given a coordinates of the bunch of the nodes, and then we focus on this link between this transmitter and receiver here. So we are given a bunch of coordinates, we are giving the path loss, we are giving the fading model, and then we want to calculate some performance metrics such as throughput or the success probability. And now, of course, after sometimes the nodes move around, and then we again have a new realization, and then we have to repeat the calculation of the performance metric again. And then same happens if the nodes move around or there is a traffic pattern change, then we have to do all these calculations again. So in my view, I would not see these three instances as the three different networks, rather than I will see them as an ensemble of networks. So when we see these as an ensemble of the networks, so it has specific advantage, because as I said earlier, the analyzing for a specific realization is not very useful, and it's very difficult. You have to do the calculation again, especially if you do the system level simulation or experiments, which are very costly and time consuming. As the realization changes, you have to redo a whole process again. So it will be helpful if we can make some statistical statements about a class of network realization. So I'll treat these and these three realization as a class of network realization, and then if we can make some statistical statement about this class of realization, that will be useful in analysis, because as I will show later, that with this such approach leads to simple analytical expression which are very fast to evaluate. Now, basically, here what we do usually, we obtain the spatial average. So spatial average means we take a large network, and then we average over the performances of these different users lying in a single realization. For example, for this user, we calculate the performance, and then we take a spatial average to obtain the performance. So this spatial average approach lists the expected values of certain performance metrics. For example, what is the likelihood of a successful transmission? Now, how can we characterize the performance of such a network? So we can use the well-established tools from stochastic geometry. So where in stochastic geometry, where the wireless nodes are denoted by these points here. So now here, for example, this is the actual deployment of base station in London. So these circles here show the locations of the base station in London. Now this is a point process, where this is a tool in a theory in a stochastic geometry, where we treat each location of the base station as a point, and then if we simulate a Poisson point process, where for example, the Poisson point process means that in a given network, the number of even given region, the number of points are Poisson distributed, and then to exclusive regions, the number of points falling in those exclusive regions are independent of each other. Now, if we simulate this Poisson point process with the same density of base station as here, then we see a realization of base station given by this Poisson point process. So as shown here in this paper 2, this reference to that, the stochastic geometry can model the cellular networks and provides a reasonable fit with the real deployments. And also a key advantage with these tools of stochastic geometry is that we can obtain simple analytical expression of several performance metrics, and also allows a system level performance evaluation, as we will see later in the talk. Now, the most previous work focused on the beam selection as a result of base station handover. For example, this reference is 1 to 4. So these papers do not focus on the beam reselection as the UE moves within the cell. Also, probably the most relevant reference is 5 here, which focus on the calculation of the beam selection and the reselection rates. But there are the key things missing in those papers, that it considers only noise. But as we see that the modern wireless networks are quite dense, so interference is a big issue. So this paper doesn't consider interference. Also, there is no beam management. What is the how you should manage the beam? How many number of beams the base station should deploy? Also, this mmWave is very sensitive to the blockages due to the high path loss. So there is no blockage modeling, and also there is no beam misalignment. As the UE move around, so there might be that it is connected to a suboptimal beam. So there is a beam misalignment. So there is no attention paid to this beam misalignment. So we will take into account all these issue, and also we will perform a system level analysis. So our key contribution that our work is probably the first mathematical optimization framework for the beam management problem in 5G. So we calculate the number of beams that maximizes the area spectral efficiency. And then we do the system level analysis of beam management using stochastic geometry. So what do I mean by system level analysis here is that, so our analysis can capture a given average speed of the mobile terminals, also called as UEs, so I will call MTs for the rest of the talk. Then mobility induced the beam alignment errors, the beam selection, beam reselections, and associated overheads. Then we can actually consider the average speed of mix of MTs. So the MTs could be pedestrian, bikes, or cars. And the mix of geometries, some cells are bigger, some cells are smaller. Then the mobile terminals are closer to the base station, or they might be at the cell edges and far from the serving base station. Also, the wireless propagation properties, which is the mix of fading blockages present in the network. So given all these things, different aspects of a network, our optimization problem yields the number of beams that provides the best spatial average rate for MTs of all types in a large mall. So if as a system, so we take the input as a system, and then we yield a single output that gives us the optimal number of beams that gives us the best spatial average. And then we show that we can represent, in fact, the key performance metric using simple analytical formulas, and which leads to these fast numerical results to evaluate this 5G new radio compliant radio access network. So basically, we study the sub-6 gigahertz or FR1 deployment, and also the FR2 deployment, and we show a systemic trade-offs among these different parameters of the network, and compare this FR1 and FR2 deployment. So this is the network model. So here the base station locations follow a homogeneous Poisson point process denoted by phi with intensity lambda, or it is the density of base stations. Now we assume an omnidirectional MT, so we can extend this word to directional MT. So which moves on a randomly oriented straight line with speed v. So this is the trajectory of the mobile terminal. So it moves in a straight line. And this mobile terminal connects to the nearest base station. So the serving base station is the nearest base station. So for example, here this red square is the location of the mobile terminal, and then it connects to the nearest base station. Now, when we have this Poisson structure of the base station, and then we have the nearest base station association, we have this Poisson-Voronoi structure given by these black lines here. And then due to the isotropy and the stationarity of the Poisson point process, we can assume that the mobile terminal motion can be along x-axis and passing through the origin. So this line is nothing but x-axis, and then each BS always has an MT to serve. So we assume a saturated traffic scenario, and then a base station serves one MT at a time per resource block, given the frequency and time. One base station serves one mobile terminal. Now, this is the serving base station, but what happens, there are the base stations located outside beyond the serving base station, and these base station here, which are the potentially interfering base stations. So this base station might cause interference to the mobile terminal here. So we take into account the interference from the base stations. Now here we show the beamforming model, where we show that we assume that a base station employs 2 raised to the power n beams. So n goes from 1 to, so it is basically 2, 4, 8, 16 beams for the simplicity of analysis. And then there is a mobile terminal. Now, for the simplicity, for the analytical tractability, we approximate the actual antenna radiation pattern, which is given by this red curve here, a red figure, to simplify the analysis. So basically, this big red curve here is the main lobe of the antenna pattern, which we approximate using a sector. So for this main lobe, the gain is given by this GM, which depends on the number of beams, n. And then these smaller curves with red curves denotes the side lobe of the antenna radiation pattern. So where this gain is the GS. So this GS, this antenna gain for the side lobe is smaller than the antenna gain for the main lobe. Then the beam width, so width of a beam is given by this phi n here. So phi n is given by 2 pi over 2 raised to the power n. So basically 2 pi is the covers the all directions, and then we have 2 raised to the power n beams. So the width of each beam in angular beam width is the phi n, which is given by 2 pi over 2 raised to the power n. Okay. Now, when we have 2 raised to the power n beams, we have 2 raised to the power n minus 1 beam boundaries. For instance, here we have 4 beams, 1, 2, 3, 4, and then we have 2 beam boundaries like here and this horizontal. So here we define the beam boundaries from edge to edge of a Voronoi cell. Now, the antenna gain is given by the, which is a function of the number of beams, is given by the GMN, which is equal to 2 raised to the power n, when this angle of the both side duration lies within this sector. Okay, so though the antenna gain increases with the number of beams, at the same time the side lobe decreases with the number of beams, which is 1 over 2 raised to the power n. So, which because of the large number of antennas or the beams, we can have a very narrow beams, and which reduces the side lobe gain.
Sorry, this is Klaus. Do you want to take some quick questions along the way,
sure,
or to wait at the end?
No. I can take questions. No problem. Yeah, please.
Yeah. So I was just wondering, on your previous slide, you said that the mobile terminal connected to the site that was closest or nearest. But I guess in reality, the UE would connect to the site that corresponds to the highest received signal strength, and that depends a lot on your beams and the way you have positioned the beams, both the beam shapes and of course where they are pointing and number of beams. And I could see here on the next slide, you actually nicely presented that you assume some beam configuration. So can you maybe try to comment, are you actually using this nearest ones, or are you actually taking the shape of the beams and the radio propagation conditions into account when you decide that?
Yes, certainly that is a very good question. That means so this is basically when we say the nearest base station association, it is basically we connect based on the average received power. So and you are saying that we can connect based on the maximum received power. So basically the nearest base station means that we take the average maximum power and we connect to the base station which provides us the average maximum power, which is the nearest base station due to the smallest path loss. But certainly it is possible. The main assumption is due to the simplicity in the analysis, because once we have this nearest base station association, we have this nice Poisson-Voronoi structure, and which can exploit the properties of this Poisson-Voronoi structure to come up with the simple analytical formula. But certainly it is possible to connect to the base station taking into account the beams, beam strength, and the other fading and other factors, and connect to the base station which gives the maximum instantaneous received signal. So that is also possible, but it leads to a lot of complications. And there have been works in traditional cellular networks where people have taken that approach, but the results show that the experience show that it is very hard to, or harder than the nearest base station association scheme. Yeah, but certainly it is possible to do that. Does that answer your question?
Okay, so you are assuming the nearest, so you are not assuming that it connects to the base station corresponding to the highest received power. So to this base station UE association, it doesn't take into account the beam patterns in your case?
No, it takes account. So as I will show later on in the so basically beam pattern means we take the average beam pattern. So basically the performance that we do is the average over all possible configurations. So what happens that when we average over all possible uncertainties, let's say fading or the locations or of the base station. So basically we connect to the, so on an average we connect to the base station, which gives on an average the maximum received power, not the instantaneous one.
Okay.
Yeah, but Sanket, when there is for instance an obstacle in then you will not connect to the closest, but to say the best signal.
Yeah, probably. Yeah. So that is true. So yeah, means that is what I have mentioned also later on, that this is might not be the best association because if we have obstacles and we have very weak signal. So yeah, but this connecting to the nearest base station, this assumption means makes life very simple in terms of analysis. So one of the key reasons to assume the nearest base station association is the simplicity that is associated with this association, but without losing much of the insight into the network and the analysis. So does this answer your question, Klaus?
Yes. Thank you. Okay.
And now here we consider the blockage model. For instance, if there is a beam from the base station to the mobile terminal and there is a building in between, so this beam might be completely blocked or partially blocked, but due to the reflections or the refraction, probably this empty might be able to still receive a signal on a non-line of sight path. So basically there is a line of sight path here shown. There is a base station, and so there is a line of sight path to this mobile terminal. To approximate this blockage model, we use the LOS ball model shown here. So basically what means that if there is a UE and within the distance of RC, we assume that there is a line of sight communication. If the base station lies outside this LOS ball, then there is a non-line of sight communication to the this mobile terminal. And then, so basically here it shows that if the serving base station lies within the LOS ball, so there is a LOS propagation. So there could be a interfering base station within this LOS ball, which also has the line of sight communication. While this base station which lies outside this LOS ball, we have the non-line of sight interfering base station. Okay, and we characterize this LOS and NLOS propagation by the different path loss exponent. For instance, for the LOS, we have the path loss between 1.8 to 2.5. And then the non-NLOS, we have the path loss exponent that is between 2.5 to 4.7. And then RC is the maximum distance for the LOS propagation. So this RC can be tweaked, and then you can have a different size of the LOS balls. And this is for the FR2, and then in FR1, we assume that there is only non-line of sight propagation, and there is no line of sight propagation due to the larger distances and the ability of the sub-6 gigahertz signals to reflect, and then you can still receive some signal due to the blockages in FR. Now the channel model, we assume a channel power gain. Hx is the channel power gain from the BS located at X to the typical mobile terminal. We assume relay fading with unit power gain. So basically the channel power gain is exponentially distributed. And then X is the distance between this mod X is the distance between a base station at X and the typical MT, which is located at the origin. And this is the standard path loss function we use for the LOS ball. Within the LOS ball, that is the distance from the base station to the MT is smaller than RC. Then we assume this function where the path loss exponent is alpha L. Well, if there is analogous propagation, then the path loss is alpha N. And this K is a frequency dependent constant where the C is the speed of light and Fc is the carrier frequency. So as we see that as the carrier frequency increases, there is this K reduces, so there is a higher path loss associated with increased carrier frequency. Yeah, so one key thing here that if this beam is pointed towards this mobile terminal only, then this MT receives the interference from this base station. If this, for example, this beam, this base station has a beam pointing to other direction, so there will be no interference, or probably the interference due to the side lobes of this base station towards the MT. But here we have the interference from the main lobe of this base station. Now there is a beam misalignment due to the mobility of the MT. For example, the beam reselection occurs during a synchronization signal burst, which is called SSB, which repeated after each duration of tau. So, for example, there will be a measurement done at the, basically what happens that the UE takes the measurement about the beam quality and connects to the best beam. So, for example, if the measurement is taken here, so the UE connects to this this red beam here at time t. But what happens that the next measurement is taken here. So the measurements are given by these crosses here. But by that time, this mobile terminal might have already crossed this beam boundary into the new beam, which is denoted by at time t dash, denoted by this blue beam. But since the MT takes measurement only here, so there will be no beam reselection here. So basically what happens, so even though this MT is in the zone of this new beam, blue beam, it is still connected to this red beam. So basically it is now connected to the side lobe of this red beam, and then there will be a smaller gain to the mobile terminal from this base station here. So what happens, so this leads to the beam misalignment due to the mobility. So the mobile terminal might move to the beam width of a new beam without handing over or without doing the reselection. Now we can characterize this beam misalignment using this equation where the probability of beam misalignment is given by this expression here, where this denominator is the mean distance between two consecutive beam reselections here. Basically, this is the average distance between this consecutive beam reselection distance. Then V is the speed and tau is the duration between these two measurements, SSB measurements. Okay, and then as we can see that if the speed increases, this the probability of beam misalignment increases. Also, if the duration between two SSB increases, then again that leads to the increased beam misalignment. Now, also the mean distance between two consecutive beam handovers or this beam reselection reduces, then the mobile terminal is more likely to cross multiple beam between two measurements, and again the probability of beam misalignment increases. So we can we can have an equivalence. We can see this equivalently. We can see this expression as a probability distribution. So which is the t is the random, capital T is the random variable, which is greater than t, and which is the exponentially distributed with mean 1 over v times mu SB. So this is nothing but the average distance between the two, the average time between two beam reselections, and then this capital T is the time between two consecutive SSB. So basically, this equation here shows assume that the time between two consecutive SSBs is exponentially distributed with the mean same as the mean time between two beam reselections. Now, due to this beam misalignment, the antenna gain of serving base station is given by this equation here. So with probability of 1 minus PBM, we connect the MT connect to the main lobe, whose gain is given by 2 raised to the power n, and with probability PBN, which is the probability of PBN, it connects to the side lobe of the serving base station. Now, the system model in nutshell is given here that each base station has for the 8 beams or 3 sectors, where we have this base station, Poisson base station, and then we have 8 sectors for each Voronoi cell. and the UE move around this line, and then these yellow circles denote the base station handovers, while this brown circle here shows the beam reselection points within the Voronoi cell of the base station. And this black boundaries here is the Voronoi cell boundaries. Now we can have the interference from a base station only if this it points the main lobe towards the mobile terminal. Otherwise, it can have the interference used by the side lobe of the interfering base station at the MT. So basically, the beams of all base stations are oriented towards their respective mobile terminals, and so the interfering base station point their main lobes in uniformly random direction. So the interference will be the interference will be from the main lobe with probability of this equation here, this phi n over 2 pi, while the interference will be from the side lobe with probability 1 over phi n over 2 pi. And then the interference power is given by this equation here. P is the transmit power of a base station, Gn is the antenna gain, Hx is the fading, and then Lx is the path loss between the base station at X and the UMT located at the origin. And then we know that the many key performance metrics are dependent on the signal to interference noise ratio, or the SINR. When the typical MT is connected to the base station location at X0 with antenna gain G0, then the SINR at the typical mobile terminal is given by this equation. So basically, the numerator is the signal power, and then sigma square is the noise power, and IN is the interference. So N0 is the noise power spectral density, and then W is the bandwidth. Now we can calculate the complementary cumulative distribution of the SINR, from which we can calculate the ergodic Shannon rate as an indicator of the throughput achieved. And then the CCDF of the SINR is nothing but the success probability, which is given by the probability that SINR is greater than some SINR threshold beta. Now, in the spatial average interpretation is that in a given realization of the point process or the network, this success probability is nothing but the fraction of the mobile terminals that have SINR greater than this threshold beta. Now, this SINR threshold beta parameterizes the transmission rate by this equation log of 1 plus beta, and then the outage probability is nothing but the 1 minus success probability. So for the FR1, we can calculate the success probability is given by this expression here. Now, the first term corresponds to the no beam misalignment. So when there is no beam misalignment, and this is the QS is the success probability associated with the no beam misalignment, and this is the probability of no beam misalignment. And then second term here is the term associated with the beam misalignment. Now, this term here is the success probability of individual cases is given by this expression. In a simple form, given that we have so many uncertainties, beam forming, blockages, the location uncertainties, fading, or path loss, given that we have a very simple expressions for the success probability. So basically, this term here is the interference from the base station. So we connect to the nearest base station, which is let's say distance r. Then the interfering base station lie at a distance from r to the infinity. So we have an infinite 2D plane. And then this interference, this term here comes from the interference due to the main lobe, and then this interference is due to from the side lobe of the interfering base station. And then we have this noise term associated with the we have signal power and then the noise power. And then R is the distance to the nearest base stations, and due to the random geometry, we have a probability density function R, which is given by this equation here. Now, similarly, we can calculate the success probability for the FR2. Again, we have the same thing, no beam misalignment case, beam misalignment case. The key thing here is the LOS ball here. We have the critical distance within which the base stations are line of sight, with the outside that they are non-line of sight propagation. So basically, the 0 to RC shows this term here corresponds to the LOS serving base station, while this term from RC to infinity corresponds to the non-LOS serving base station. Now, these are the respective noise terms when there is a LOS serving base station and an LOS serving base station. And then again, the interference from the interfering base station is due to the main lobe interference given by this term here, and then the side lobe given by this term here. And then these terms here gives the interference from the LOS base station. For example, this base station lying within the LOS ball. And this term here is the interference from an LOS base station, which is the base station. And then again, when the serving base station is outside this LOS ball, the interference from the non-LOS base station is given by this expression. So we can see that even though we have this so many factors in the system model, we can these equations beautifully captures the individual effect of these different effects of beam misalignment or the LOS or NLOS propagation or the noise or the fading quite beautifully, and then it gives us insight into the analysis. Now, the ergodic Shannon rate is given by this expression, W times expectation average. This is the average, and then log of 1 plus minimum of SINR plus Qmax. So Qmax is the maximum SINR achievable in practice due to the RF imperfections and modulation schemes. And then the final expression of the ergodic Shannon rate is given by this expression here. Now we have the overheads associated with the beam reselection when the, as if you remember, as the mobile terminal moves within the Voronoi cell of the base station, we have this beam reselection happening at these beam boundaries denoted by this dashed curve here, 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 here. And then we can calculate the number of beam reselections per unit distance. So given the distance, how many beam, basically that is nothing but the linear intensity of the beam reselection. And then we can use the Campbell's theorem from the stochastic geometry to calculate this linear intensity of the beam reselection. So basically, this gives the expression of the beam reselection given the our assumption for the 2 raised to the power n beams and then Poisson point process of intensity lambda. The linear intensity of beam reselection of the typical MT moving in a straight line with speed is given by this expression here. So here lambda is the density of base station and 2 raised to the power is the number of beams. So as we increase the density of the base station becomes smaller, and then the size of the each beam width of the each beam sector is smaller, and there will be higher number of the beam reselection. So the linear intensity increases with lambda. And then the times intensity, which is the beam reselection per unit time, is given by this expression. So we have another factor, speed V. So as the MT moves at very high speed, then it crosses the boundaries of multiple beams given for compared to the smaller speed. So the intensity of the beam reselection increases. Okay, I will skip this idea of the proof due to the lack of time. Now, if we consider the beam reselection, then we have the beam misalignment. So as we saw that the beam reselection happens only when the mobile terminal makes the SSB measurements denoted by the crosses here. So if we so there could be the possibility of beam reselection skipped due to the because if there is a beam, if this mobile terminal crosses the boundary between two SSBs. When we take into this beam misalignment into account, we have the modified equation for the intensity of beam reselection given by this expression, where tau is the duration of the between two SSBs, and this is the time intensity of the beam selection without the beam misalignment. And then the time of stay, it is the average time spent by the mobile terminal in a beam, which is nothing but the inverse of this time intensity of beam reselection. And similarly, we have the base station handovers at these boundaries of the Voronoi cell, so denoted by these yellow circles. As the MT moves along this line, then there are the base station handover from this serving base station to this new serving base station at these boundaries. And there is a classic result by Professor Baccelli that which gives us the intensity of this cell boundary crossing, again, which depends on the density of base station and then the speed of the mobile terminal. And these two operations of beam selection after each beam handover and then beam reselection within the Voronoi cell of the base station leads to the time overs TC and TB. So which is due to these periodic SSB measurements and the receiver processing time and then handover interruption due to the cell switch during the base handover. While during the beam reselection in the Voronoi cell, we have this time overhead of TB due to these periodic SSB measurements and the receiver processing time. So the total average overhead per unit time is given by this expression, where this is the intensity of beam reselection and the overhead per beam reselection, and this is the intensity of base station handovers, and then this is the TC is the time overhead associated with each base station handover. So this is the overall overhead TO. And then the effective area spectral efficiency is given by this expression here. Lambda is the density of base station, Rn is the ergodic Shannon rate, and then 1 minus T0 is the effective time that is available for the data transmission. Okay, and then the final problem is ultimately to find this optimal n and star, which maximizes this effective area spectral efficiency. So these are this effective area spectral efficiency basically captures all the different factors, beam misalignment, fading, path loss, or the LOS, or the blockages effect into this one single equation. And then we can optimize over n to find the optimal number of beams. Now we have these network parameters here given by for the FR1 deployment and FR2 deployment. So for FR1, we usually have a higher transmit power due to the larger cell sizes, and FR2 due to the smaller cell sizes, the smaller transmit power is sufficient due to the beamforming gain as well. So as we see, the intersite distances for FR1 are larger than the intersite distances for FR2. Now the intersite distances, we can calculate, there is a connection between the intersite distances and the density of the base station. So basically this intersite distances, we can approximate as a equivalent ball of with the same average area of these cell sizes. And then we can calculate the intersite distance using this formula here, where lambda is the density of base station. So if the density is higher, then the intersite distances between are smaller due to the dense deployment of the base stations. Now this is the key result of for FR2, where we plot the effective area spectral efficiency against the number of beams. Basically, number of beams is 2 raised to the power n for different intersite distances, and then the different speed of the mobile terminal. So as we see, there is a trade-off associated with n, and there is an optimal number of beam exists, or depending on the IST and the speed of the mobile terminal. So basically, what happens that if you increase the number of beams, it leads to increased beamforming gain due to the narrower beams, and also it reduces the interference because the narrower beam, because the narrower beams means there is a smaller probability that the interfering base station are pointing their beams towards the mobile terminal. No, but there are some costs associated with this increasing the number of beams. There will be higher number of beam crossing. Also, it increases the probability of beam misalignment. So due to this effect, and there is a tussle between these parameters, and we see the optimal number of beams here, the optimal effective area spectral efficiency with the number of beams. Also, for a given number of beams, or for a given n, if the speed of the UE increases, the mobile terminal moves very fast, and it crosses more number of beams and performs higher number of base station handovers, which increases the overhead associated with those handovers. So that reduces the time available for the data transmission, and then reduces the area spectral efficiency. Okay. Now for the same also, if we see for the different ISDs, the intersite distances, so there is a trade-off associated with the ISD. For instance, here we show that ISD for 75 meter, and then this is the ISD for 125 meter for the same speed. So for smaller n, we see that for the smaller ISD, the effective area spectral efficiency is higher than the case where there is for the larger ISD. This happens because at smaller n, the smaller ISD has a dense network and because of that dense network, there is a smaller path loss to the serving base station, so which benefits the area spectral efficiency. But as we increase the n, the overhead increases with the smaller due to the dense deployment of the networks, and then for large n, we see that the area spectral efficiency is larger for the larger ISD. Again, this figure shows the comparison between FR1 and FR2 for different ISDs. So here, key thing is that there is a trade-off again between FR1 and FR2. FR1 are this dashed, FR2 are this dashed curve, and FR1 are the solid curves. So here, FR2 gives the higher, always gives the better performance than FR1, irrespective of n. But there are a trade-off here. There is a crossover of these curves due to the trade-offs associated with the LOS ball, because what happens in FR2, we have this line of sight distance until certain distance or until certain point, and then after that, there is a non-line of sight communication. So there is an interplay between this line of sight communication and then inter-site distances, depending on how many base stations fall within the LOS ball and how interfering base station within the LOS ball. And due to that, this thing, we observe this crossover of these curves between FR1 and FR2. Note that this FR1, we assume just no line of sight communication, while in FR2, we have line of sight communication as well as no line of sight communication. Okay, I'll skip this because this is basically the same thing where we plot the success probability against the number of beams. So the trends are similar compared to the previous figure. And here we plot the time of stay of a mobile terminal in the beam. So as we see that the intersite distance increases, the time of stay increases, or basically for 1,000-meter ISD, we have the highest time of stay, while as the ISD decreases, then the time of stay of the mobile terminal within the beam reduces because of the dense deployment of the smaller cell sizes of the due to the dense deployment of base stations. Now, on the other hand, so our motivation was to see how this stochastic geometry can be used in 3GPP standardization process. So basically, this cycle shows the typical process of in 3GPP standardization. So you start with the technical problem, then given the technical problem, you do research and inventions. And then based on that research and inventions, you do the exploration using probably system level simulations, and you try to validate the theoretical analysis or the research that you have performed. Basically, and then we have this engineering aspect where we do the practical experiments and then see how close the actual research and the system level simulations are. So that usually leads to the patterns. And then we have the solution, and then we have again new technical problems, and this cycle repeat. So basically, we operate in this here in this shaded blocks, the technical problem, research and inventions, and then exploration and validation. To be specific, that this is the scope of our work, where we have the model of a system, and then we have the construction of approximate theory. For example, model, we use the Poisson structure of the base station locations, and then we have this approximate theories where we use the probability of beam misalignment, then considered only average beams reselection or the base station handover rates. And also there was approximate antenna gain formulation. Also, as Klaus pointed out, we had this approximate base station association scheme. So we have these approximate theories here, and from those approximate theories, we make some predictions. For example, in our case, the prediction is what is the optimal number of beams that maximizes the area spectral efficiency. And using these theoretical predictions, we would like to see in the future that, okay, if we make the system level simulations, and then how close this theory or these insights obtained from theory are close to the system level simulation, and then probably we can improve the theory based on that. So basically, our goal is to complement the system level simulations, which is shown here. Basically, here what happens that we have this incremental process for evaluation. So the numerical formulas that we had, this analytical expression, those could be solved using within seconds or even and minutes, compared to the system level simulation, which usually take the hours or the days to run. So basically, you have a new realization, you do the system level simulation, and then you have to wait for a long time. So basically, our goal is to complement this system level simulation. So using these formulas, analytical formulas, we can gain crisp insights into the analysis. And okay, we can say, okay, these are the optimal number of beams that we obtained using theory, and then we can basically choose those particular set of parameters to start our system level simulation. So that reduces the search space for the system level simulation. Now also, if we move to actual implementation, which also the experiments which requires days or weeks of works. And then to conclude the concluding remarks, that we had a system level stochastic geometric model for these 5GNR, where we captured the essential scenario characteristics such as the operational frequency, blockage characteristics. Then we had these technological features, which is the beamforming configuration or the delay overheads. Then we had a network deployment choices such as the intersite distances, the carrier bandwidth. So basically we consider different aspects of the system. And then using that, we calculated the optimal number of beams that maximize the area spectral efficiency. And then we particularly, although our model is quite general, so we particularly focused on a dense urban macro and picocell scenario for FR1 and FR2, which help, and then we capture the various systemic trade-offs between the ISD's path loss, interference, and overheads due to the beam management. And ultimately, we show the effectiveness of stochastic geometry-based tools. So we could do the system-level analysis for this beam-based radio access network. And also, as I said in the second part of the presentation, that it can be used to contribute to and accelerate the standardization process by giving the crisp insights into the system-level simulation or the experimental setup. And there are few certain directions. Certainly, means there are we had many approximations, so we can improve the modeling to in the future to come up with the more accurate modeling of the network. For example, we can have a multiple panel UEs, so multiple antennas at the UEs. So as of now, we assumed only single antenna or omnidirectional UE. Then we can have a base station or mobile terminal grid of beams, which to capture the effect of 3D effects, beam azimuth, basically height of the antennas. So as of now, we assume only 2D plane, so we can have a 3D deployment of the base station and analyze that network scenario. And also, we can have the refined intercell and intracell mobility overhead. So as of now, we assume the calculation of the average intercell and the intracell handover rates. But now we can actually calculate the distribution, how the more, which gives the fine-grained insight into the effect of this mobility on the overhead associated with the mobilities. And then later we would like to compare our analytical results and the prediction with the system level simulation with the help of our Nokia Bell Labs colleagues. Thank you. Yeah.